Namaskar, Shesi. Only does your cameras are on. That's it. So we are starting with the new topic. Okay, so next is magnetic effects of electric current. But before that, we see what happens to a magnet or what is a magnet. Okay. So as we see, as we have seen, that magnet is a substance which has the property of attracting iron objects. You see any magnet, so any magnet has the property of attracting iron object, attracts all the iron object.
Sir,
Yeah.
sir, I have joined through two devices, sir. So my camera, I'll on it. Like, just don't remove the other account, sir. Thinking there are two chassis, sir.
Okay.
Because my mic is not working on my laptop, sir.
Okay, fine.
Yes, sir.
So let's see, magnet. Magnet, it attracts iron and some other substances. So what are those other substances? Can you name some other substances which are attracted by iron? Which are attracted by the magnet?
Sir, steel?
Nickel, cobalt, steel. These are the materials which get attracted by a magnet. And such substances, they are called as magnetic materials. They are magnetic materials. Not all the substances are attracted by it. Now, if you see a magnet, so every magnet has two poles. Okay. So every magnet, it has two poles, and we call them as north pole and south. So the two poles of the magnet, north pole and south pole, they are separated by some distance. They are located towards the end of the magnet. So which pole do we call as the north pole and which pole do we call as the south pole? Can we call any pole to be the north pole?
No, sir. The opposite ones we call it as north and south.
So can I call this pole to be north and this one to be south? On what basis do we call them as north pole and south pole? So the reason is that if you suspend a freely magnet, if you suspend a magnet freely, so it will always align itself towards north and south. Okay. Every magnet, if you just take this magnet and tie it with a string, okay, tie it with a string and then make that string attached to a stand. So if you rotate this and leave it, so this magnet always settles in the north-south direction. Okay, it will always settle in the north-south direction. So the pole of the magnet point toward north. Let's say if this pole point towards north, so this will be the north pole. If this pole point towards the south, so this will be the south. Okay. So the pole which always point toward north, this will always point north. Okay. This will point south. Why it happens? As our earth itself behaves as a magnet. Our earth behaves as a magnet, and it appears as if there is a big magnet inside the earth. However, there is no such big magnet inside the earth. Okay, but it appears as if there is a big magnet inside the earth, which is causing a magnetic field, which is creating a magnetic field on it. So we have understood that every magnet has two poles, and which will be a north pole and which will be a south pole. Okay. Now we see another thing relating to this compass, to this chapter, that is a compass needle or magnetic compass. So I think all of you must have used this magnetic compass, or not used, then you must have seen a magnetic compass.
Yes, sir.
Okay. So a magnetic compass, it is a needle. It is a compass, that means it has. Okay, let me show you about the magnetic compass. Let's see. Let me show you how does you can also in your even in your phone you have a magnetic compass. That is a that is not this one. That compass is working principles are different. So magnetic compass, if you see, it is a dial-like structure. See this one. So all these are magnetic compass. Okay. So you might have seen some of the watches, they also show this magnetic compass. Okay. Your Android phone also has a magnetic compass. So here this is a magnetic compass. How it works, the needle which is there in between, it is free to rotate. Okay, the needle in between is free to rotate. It can rotate freely. Now there is a small magnet attached to one of its ends. Okay. So at one of its ends, this needle is actually a magnet. So when this needle is a magnet, such that this is the north pole of the magnet and this is the south pole of the magnet. So wherever you keep this compass will always point in the north direction. So this part of the needle, it will always point in the north direction, right? And the other part will always point in the south direction. Okay, if you have not used it, you can open your phone, search for the magnetic compass, and it will show a magnetic compass. You can use it. So at even at your location, it will show you where is the north direction, where is the south direction, right? So now what will happen? So all of you are understood that this magnetic compass will always point in the north-south direction.
Yes, sir.
Okay. Now, if suppose at some time this magnet, what will happen if I bring a magnet near? Now, if I place a magnet near it, so what will happen? Again, will it show in the north-south direction or will it show somewhere else?
It will show somewhere else, sir, because here north and north are likely facing, sir. So there will be a repulsion.
Yeah, there will be a repulsion, and now it will not show you north and south. Okay, so any deflection in the compass needle, it means that there is a magnet near it. Okay, if you see any if you see any observe any deflection in this magnetic compass, it means that there is a magnet nearby. Okay. So it can be of various types. Either you can take it that permanent magnets, which are your alnico magnets. Another point, your permanent magnets, they are made up of alnico. Okay. Alnico means alloy of nickel and cobalt. Permanent magnets, they are made up of nickel, cobalt, steel. These are the materials of which we make the permanent magnets. Now let's see the next one. So up to now, this was magnet. How people searched for the magnet. If you go for the history, how we started with the magnetism, how did the magnet start? So there are various stories that how the magnet is, how it worked, how it came to the society. There are various stories, but stories don't have any proof. Okay. So there are no proof how the magnet enters our society. Now let's see the next part. That is a very important topic of this chapter. That is experiment of Hans Christian Ørsted. This is an experiment of Hans Christian Ørsted. So this fellow Hans Christian Ørsted, he was actually performing some experiment relating to electric current. He was not performing any experiment for this magnetism. Okay, it was by mistake that he found out something about magnetism. Okay, but basically he was performing some experiment regarding electric current. So what he observes? He observes that, let's say this is the circuit. Let's suppose you have the key and here you have the switch. So he was performing some of the experiment with this electric current, but by mistake he had placed a compass needle near it. So this was by mistake that he placed a compass needle just near this. Okay. So as he saw that it always points in the north direction. Now when he switched on, when he put this switch on, so at that time what happened? He observed this needle showing deflection. So he was not bothering about this needle at that time. He was bothering of his experiment. But suddenly he saw that the needle is showing deflection. When he turned on the key, he found out that the needle shows deflection. If it turns off, then he sees that there are no deflections. Now again, the needle points in the north direction. So every time the needle is pointing in the north direction, but when we switch it on, so the needle gets deflected. It gets deflected to some other direction. So he tried it many times, and every time he observed that yes, the needle shows deflection only when we press this key, only when the circuit is on, only when some current is passing through it, then only it is showing deflection. Now he placed this to the inside of this circuit. He placed it over here. And now again observe that yes, what deflection will it show? So again, it showed the deflection, but the deflection now was in the opposite direction. Okay. So he observed that the deflection is now in the opposite direction. Okay. It's not in the same direction, it is in the opposite direction. Okay. So from here, he observed that since a magnetic compass will always show deflection if there is a magnet. Okay. But there was no magnet. He searched everywhere nearby. There was no magnet. Okay. And everything is happening just by this current. So that means there must be some relationship between current and magnetism. Okay. So he found out that the source of magnetism is the current. When the current is passing through this wire, then some magnetism is being generated by this current. So what was the conclusion of his experiment? He found out from here that origin of magnetism, where does the magnetism originate? So magnetism originates from current. Okay. Current can form magnetic field. It can create a magnet. It seems as if there is a magnet nearby. Now, after this experiment, then further more experiments were carried out to study about magnetism. So everyone has, I hope everyone has understood up to here. What are magnets? What are its poles? What is a magnetic compass? Everything. Hence, Christian Oersted's experiment.
Understood, sir.
Yes, sir.
Now, the next concept was magnetic field. So, why we are going to discuss this magnetic field? Is there, suppose there is a magnet? Okay, I have a magnet over here. Which is having its pole as, let's say here it has north pole, here it has south pole. And if I place some pieces of iron, if I place some bits of iron over here, okay, so they all will get attracted towards this magnet. All the iron pieces, they get attracted towards the magnet. So that means this magnet is applying some force on this. Okay, the magnet is attracting, the magnet is applying some force. Now it was thought that how can the magnet attract these objects without any physical contact? There is no physical contact between the magnet and the iron nails. So how is the magnet attracting these iron nails? Okay, if the same iron nails are placed very far off, so there is no attraction. If you place these iron pieces too far from it, so there is no attraction. If you place them nearby, there is attraction. So what is happening over here is that it was thought of that the magnet, it creates a field around itself. Okay. So the region around the magnet creates a field or space around it. Let's see. Okay. So it was supposed like this that the magnet, it has created some space around it, some field around it. So if you place any object or any iron object in this field, in this area, it is going to attract them. Now the space around this magnet that was there, this space was called as magnetic field. The space around a magnet where we can feel its presence. So the space around a magnet where we can feel its presence is called as magnetic field. So what is magnetic field? It is the space around the magnet. Where its effect or where its presence can be experienced. Okay. So I hope you have understood about this magnetic field.
Yes, sir.
Okay. Now, since this magnetic field, it can attract iron objects, but it can repel the poles of magnet, right? It also has the properties of repulsion. Okay. So that means there is some directional behavior of this magnet, and hence this magnetic field must be a vector quantity. This is not a scalar quantity. This is a vector quantity. It has its magnitude as well as direction. Magnetic field has its magnitude as well as direction, hence it is a vector quantity. So how it was assumed that this magnetic field is a vector quantity? See, you have studied all this in all this. At least once you have studied in your school, you might have studied all this.
Yes, sir.
Okay, but is it the same thing you have studied the same way? I don't think. See, now inside this magnetic field, what will happen? How we thought that it is a vector quantity. Just one region was this deflection of the compass. The compass needle, it shows deflections into opposite directions. Okay, which depends on the position. If I place the compass over here, it shows deflection along this direction. If I place a compass needle over here, it shows deflection along this direction. So the deflection of the compass needle, it is along two different directions. Hence, we say here that yes, magnetic field must be a vector quantity. And to justify this, we place here compass needle at various points. Okay, so here we place the compass needle, it points along this direction. Here we place the compass needle, it again point along this direction. So if I place a compass needle over here, it point along this direction. Okay, so the directions of deflection of the compass, it is dependent on the position where we are placing it, right? So that means in this area, at this place, the magnetic field has some direction. At this place, the magnetic field has some direction. At this place, the magnetic field has some. Okay. So the magnetic field at every place, it has different directions, right? So if you place the compass needle near the south, it shows its deflection along this direction. So now we see that the magnetic field is a vector quantity, right? Understood, everyone?
Sir, I did not
Now we'll repeat.
understand you showed in the magnetic fields.
Yeah,
Sir, I did not understand this what you showed, sir.
this is the compass needle. If you place your compass needle over here, so the compass needle will point along this direction. Okay.
Yes, sir.
If you place,
That's what I'm not understanding, sir. Like, on what basis are you like saying it will point on which direction? I'm not understanding, sir.
this was experimentally done. You place a magnet, you place your compass needle at various places. Okay. So your compass needle point in other directions at different places. So that means magnetic field at this place, magnetic field at this place, magnetic field at this place, they are having different directions.
Okay, sir.
Okay. So then we came to representation. How can we represent the magnetic field lines? So next are representation of magnetic field lines. How can we represent the magnetic field lines? See, so the magnetic field lines, they can be represented. Magnetic field can be represented with the help of magnetic field lines. Okay. So magnetic field, it is represented by magnetic field lines. Okay. So if you are asked a question that do the magnetic field lines really exist? So what will you say?
No, sir.
What will you say about the magnetic field lines? Do they really exist or not?
Sir, they are
Yes,
imaginary lines.
they are imaginary. They are just a representation. Okay. Magnetic field lines, they are a representation of the magnetic field. They are not real. Okay. We are trying to represent the field in this area with the help of the magnet, with the help of this magnetic field lines. So see, uh, I hope you would have done that experiment of iron filings.
Yes, sir.
Okay. So is there anyone who has not done? Okay, iron filings. Let's see. Magnetic field lines with iron filings. How does it look like? Just wait. I'll show you the magnetic field lines with iron filings. Let's see. So if you try out to do this experiment, you will find something like this. If you have ever tried it out, okay, you will see the alignment of the iron filings like this. So Rene, have you done this experiment of the iron filings?
Yes, sir.
Okay. So that's very good that all of you have done this experiment of iron filling. So that means you might have observed all this in detail, in really. So as we find here, these seem to be some lines, and hence we use magnetic field lines. Also, if you want to define magnetic field lines, so I can say that magnetic field lines are imaginary lines. They are imaginary field lines drawn around a magnet. Field lines drawn around a magnet also. So what is the direction of the magnetic field lines? Okay, the direction of the magnetic field lines, it is taken as the direction in which a magnetic compass will point. Suppose I place a magnetic compass over here. I place a magnetic compass here. So in which direction will that point? That is the direction of magnetic field lines. So in this picture, you cannot find the direction. Can you see any direction of the field lines?
No, sir.
No. So for finding the direction of the field lines, we take the direction of the magnetic compass. The direction in which the magnetic compass is. Okay. So magnetic field lines with directions. Let's see. Let's see. So as you can see here, the magnetic field lines, they originate from the North Pole. Okay. They originate from the North Pole and they enter the South Pole. So how we got this direction? What does this direction represent? Okay. So this direction, it represents, if suppose I place a compass over here, if I place a compass at this point, so the compass needle will point along this direction. Okay. If I place a compass needle over here, so this compass needle will point along this direction. If I place a compass needle at this point, so it will point along this direction. So I hope you have understood what is the meaning of the direction of the field lines.
Yes, sir.
Now let's see the properties of the field lines. This is a very important question. Properties of magnetic field lines. Okay. And if anyone remembers, so can tell those properties of magnetic field lines. I am giving you just 1 minute. Think of the properties of field lines. Think of the properties of the field lines. I need 4 properties. So just tell the properties of the field lines. Okay, so I will
Sir, I
start
don't
one by
think I have learned about the properties of magnetic field lines, sir.
Okay, you have not learned. Okay, we will start one by one and let's see who all can tell the properties of the magnetic field lines. Dhruv,
Yes, sir.
okay, so can you tell the properties of the magnetic field lines?
No, sir, I don't know.
Okay, you don't know. So you have not done this chapter?
No, sir, not yet.
Okay, so let me tell you the properties of the field lines and then after that I will be asking you all. Okay, so just pay attention. This is a very important question as it is there in the syllabus every time. Every time you find a question from this. So the properties of the magnetic field lines, the very first property of the magnetic field lines is that magnetic field line goes from the north pole to the south pole when outside the magnet. So you can say that outside the magnetic field lines move from north pole to south pole. And that is what is drawn in the previous diagram. See here, the magnetic field lines, they are moving from the north pole and entering the south pole outside the magnet. Outside the magnet, the field lines are moving out of north pole, entering the south pole. And inside the magnet, the field lines, they move from south pole to the north pole like this. They continue moving from south pole to north pole. So the magnetic field lines, they form closed loops. They outside the magnet, they are moving from north pole to south pole, but inside the magnet, they are moving from south pole to north. So here, magnetic field lines goes from south pole to north pole when inside the magnet. Okay. Now see let's see the next one. The magnetic field lines, they appear as concentric lines. Magnetic field lines appear as concentric lines and two lines never intersect each other. And no two lines intersect each other or two lines never intersect each other. You will not find intersection of two lines. In this diagram also, you cannot see that no two field lines are intersecting.
Sir, what do you then mean by concentric lines, sir?
Concentric, that means lines with the same centers. Okay. or you can say they form closed loops. A better word will be they form closed loops. Okay, so magnetic field lines appear as if they are concentric lines and no two lines intersect each other. Okay, so what will happen if I say the two magnetic field lines intersect each other? Suppose if I draw the magnetic field lines like this. Let's say this is one of the magnetic field lines. I draw the second field line like this, and let's say this be the magnetic field line. So this magnetic field line is intersecting. Here I find the intersection of the two lines. So it means that if you suppose they are intersecting, suppose they intersect, so it would mean that if I place a compass needle at this point, now if I place a compass needle over here, so this compass needle should point in two directions. Okay, at the same place, at the same time, the compass needle should show me one direction along this, and it should also point along this. So is it possible for the same compass needle?
There'll be a deflection, right?
Yeah,
There might be a different deflection, right, sir?
deflection there, but then time will be different at the same time, at the same place. Is it possible for the compass needle?
No,
Not
sir.
possible.
It's not possible. Okay, so deflection can come by the variation of the magnetic field. If the magnetic field changes, then you have any deflection. Okay, so it is not possible for the magnetic compass to point in two different directions. Okay, you might be able to write
Sir, you
with
mean
both.
at the same time or?
Yeah, at the same time and at the same place. Both.
Okay, sir.
Okay, so is it possible anywhere?
No, sir.
No, sir.
No. You can't see your front and you can't see your backward at the same time. Either one. Maybe you can see, but this compass can't. Compass will always point in one direction. Okay. So this due to this property, we say that magnetic field lines they do not intersect, or no two field lines intersect each other. Now, fourth one, the magnetic field lines, they are closer to each other when they are near the magnet. When the magnetic field lines are near the magnet, then they are closer to each other, but become farther from each other when they are far off from the magnet. So as is relevant from the diagram, you can, if you see this, look up this area. So in this much of area, you have 1, 2, 3, 4, 5 field lines. Just in this much of area. If you draw the same area over here, if you consider the same area over here, do you have the same number of field lines which were there?
No, sir. There's space between.
Okay, so they are spaced. So the relative closeness of the field lines near the poles, you will find that the field lines are very close to each other. But away from the poles, you will find that the field lines very far off. If you draw off over here, so over here you will still find less number of field lines. There are still less field lines at this point. Okay. So I hope you have understood about this point also. Magnetic field lines are closer to each other when they are near the magnet, but become farther from each other when they are far from the magnet. Then the last point, it says that closeness of the field lines shows the strength of magnetic field. Relative closeness of field lines shows strength of magnetic field. If you find somewhere the magnetic field lines are very close to each other, okay, so in that area the magnetic field will be strong. If you find somewhere the magnetic field lines they are far apart, so that means in that area the magnetic field will be weak. Rene, Rene, are you there?
Yes, sir.
So all your cameras are off. Rene, Molish, and Mira, Harshit. So just go through all these 5 points. If you have any doubt regarding any of the points.
Sir, what do you mean by strength of magnetic field, sir?
Strength of magnetic field, how strong the field is over there.
Is it the
Sir,
force between the lines?
Yeah?
Sir, is it amount of force between any two or more lines?
No, not between any two lines. What it means over here, if I place and suppose let's identify these two, place A, place B, and place C. Okay. So if I place an iron object in region A, I place an iron region in B, I place an iron object in place C. So at which place will it experience more force?
At place C.
So at place C or B?
B.
At B, because at the place B you have a stronger field.
Yes, sir. It's more close to the magnet, sir.
Yeah, the not more close to the magnet. The field lines are very close to each other. Even if you see inside, outside the magnet also. So here you find the field lines to be something like this, which are almost uniform. But near the poles, they are very strong. So if you see just over a small area over here, see how many field lines are there. And if you take this much area over here, so you can identify how many field lines are. So that's why the magnetic field is stronger near the poles. So just go through all these 5 points. In the second point, you can also add magnetic field lines form closed loops. Form closed loops. Okay. So who will tell me? Okay, Veera Harshit, can you tell me all the properties of the magnetic field lines?
So I'm still noting it down.
Okay, whatever you remember about them. Just speak of whatever you remember.
Magnetic field line goes from North Pole to South Pole when outside the magnet.
Okay. And
Magnetic field line goes from South Pole to North Pole when inside the magnet.
okay. And
Closeness of field lines show the strength of magnetic field.
okay, closeness of the field lines they represent the strength of magnetic field. And
That's it, sir.
that's it. Okay, so that's very good. You have said something. Uh, we'll say then Rene. Rene will tell.
So all of them are like the ones he didn't mention.
or whatever you remember out of them.
Oh, the closeness of the magnetic field and shows the strength of the magnetic field. The magnetic field lines form closed loops.
Mhm.
The magnetic field line goes from North Pole to South Pole when outside the magnet, and South Pole to North Pole inside the magnet.
Mhm.
And the magnetic field lines are closer to each other when they're near the magnet, but become farther from each other when far away from the magnet.
Okay, so that's nice. Okay, so Rene has said, Hasnita.
Yes, sir.
Okay, can you tell?
Yes, sir. Outside the magnet, magnetic field lines go from north to south, north pole to south pole. Inside the magnet, magnetic field lines go from south pole to north pole, and they form closed loops.
Mhm.
Magnetic field lines appear as concentric lines, and they don't intersect.
Mhm.
Magnetic field lines are closer near the magnet and farther, and vice versa. And the strength of the magnetic field is stronger near the poles.
Okay, so I think almost everyone has done. Saryu, ready? Can you say the properties of magnetic field lines?
Yes, magnetic field lines go from north to south pole when outside the magnet,
Mhm.
and the lines go from south pole to north pole when inside the magnet. The closeness of the magnetic field lines determine the strength of the magnetic field, and the lines never intersect and appear to be concentric.
Okay. So now the last question that we will be completing today, you will draw the magnetic field lines of a bar magnet. The magnet that we just saw is the bar magnet. Okay. We just saw the magnet, we draw its field lines. So those field lines, they are the field lines of the bar magnet, right? So these were the field lines of the bar magnet. So quickly today, everyone will draw the magnetic field lines, keeping in mind the point that we have discussed. Okay. So draw these magnetic field lines and just show it. After that, you may exit the class. Once you show all the your diagram of the field lines, you can exit the class. Or if you have any
Sir,
doubts, you
can
can
you show
stay.
the diagram once more?
Yeah.
Can you show the diagram?
No, you have to draw it on your own. That's something like a 5-minute quiz for today. Without any help, you need to draw, show it, and then after that, if you have any doubt or any wrong, so you will do it again. Mehak, have you done?
No, sir, I'm doing one.
Okay. Dhruv,
Yeah, sir.
okay. Are you drawing or have you done it?
Sir, I'm doing it.
Okay.
Sir,
Yes.
sir, can you quickly check mine, sir, because my battery is about to go away, sir. I mean, sorry.
Okay. Okay, so you can show it.
Yes.
Just wait for 1 minute.
Yes, sir.
North, south. No, beta, it's wrong. See, at the south pole, you have made the magnetic field lines moving out of the magnet. Rather, they should be moving inside of the magnet. Check out. You have made it wrong near the south pole.
So once can you check mine?
Wait.
Sir, I didn't get you, sir.
If you see at the south pole, near the south pole, the direction should be opposite that you have made.
Sir, outside the magnet, it's from north to south. No, north to south, right, sir?
North to south, so it should be entering the south. Yours seems to be moving from south to south. It is moving out of south.
No, sir. It's correct only, sir. The arrow
Okay.
marks are good.
Okay, just see this diagram then. Again, see this diagram.
Okay, sir.
Just wait.
जो बात बोल रहे हैं कुछ सुन लीजिए तो हम जो बोल रहे हैं जो कंपनी हमें ज्यादा फायदा दे रहा है रहेगा पकड़िए ये मत सोचिए कि हम दोनों को मर्ज करके मतलब एक को तो चुनना पड़े थोड़ा बहुत तो टुकड़ाएगा
Okay, see this.
वो भी ज्यादा दिन न रहेगा
The field lines, they are like this. They are entering the south pole.
Okay, understood, sir.
Okay,
Yes.
understood? And in this, even in this also, this one is incorrect. You should make it like this. Entering the south pole. Everything like this.
And at the north pole, sir, it will get away from it, right, sir?
Yeah, at the north pole, the field lines will get away.
Yeah, right. Okay, sir.
Sir, can you see mine? I'm done.
Sir, may I
Okay.
leave?
Yeah, you may. So
Thank
who is
you.
showing now?
Sir,
Mehak. Okay. So Mehak. Fine. Okay, Mehak, it's correct. You will.
So can you
Sir, could you please see mine?
So can you see mine?
Just one by one. Okay. So I'm looking for it. Saryu. Let's see for Saryu. Okay. Okay, Saryu, yours is correct. Maybe.
Sir, may I send you the picture on WhatsApp right now?
No. I don't go forward. So just make it. It will take just for some time, okay, and I will check for everything. Okay, this one is also correct, but try to make that the lines do not intersect. Okay, just like in near the north pole, they seem as if intersecting. So try to make them as if they are not intersecting. Okay, Vedika, you make it. Okay, then Monish. Okay, who's Hasnita is showing? Hasnita and Manan. Okay, Hasnita, it's correct. You may leave.
Thank you, sir. Bye, sir.
Then Manan. Okay, Manan, yours is also correct. Tanishka, yours is also correct. Correct. And
So
this
which
Monish is also correct.
Okay, sir. Thank you, sir.
Okay. And this one, Veera.
Thank you,
Veera
sir.
okay, Veera, just remain. I'm checking yours. Veera, you're not supposed to. Veera, you're making intersections. Do not make intersections, right? Make them clear.
I do too
Rene?
many lines, sir. That's it.
Okay. So decrease them. Rene, your figure is not okay. Now it's okay. Okay, Rene, it's correct. You may leave. And this
Thank you,
one, Dhruv. Okay, Dhruv, yours is also correct. Okay. So bye everyone.
Thank you, sir.
Thank you, sir.
Bye.